Intro. Let's get started. Directory overview. Before we jump into the code, let's understand our working directory. Our projects are organized under Piscine COO, with each exercise in its respective subfolder ranging from X00 to X05. This structure keeps our work organized and easily navigable. Now, onto the coding exercises. Discuss the ft_put_your function in detail, explaining how write is used to output a character. X01 ft_print_alphabet.c explanation. Moving on to exercise 01, ft_print_alphabet. This function loops from A to Z, printing each letter. We initialize a char variable A with 97, the ASCII code for A, and increment it inside a while loop until it exceeds 122, Z's ASCII code. Explain the loop's logic and the use of ASCII values. X02 ft_print_reverse_alphabet.c explanation. In exercise 02, we reverse the alphabet, using a similar structure to X01 but starting from Z and decrementing the value. This showcases the versatility of loops and working with ASCII values in reverse. Detail the adjustments made to reverse the alphabet printing. X03 ft_print_numbers.c explanation. Exercise 03, ft_print_numbers introduces us to numeric characters. We loop from 0 to 9, printing each digit. This exercise highlights the concept of iterating over numeric characters, bridging the gap between numeric values and their character representations. Discuss the straightforward loop used for printing numbers. X04 ft_is_negative.c explanation. Next up, exercise 04's ft_is_negative function demonstrates basic conditional logic. It takes an integer, checks if it's negative, and prints n or p accordingly. This function uses an if-else statement, a fundamental programming construct. Break down the conditional logic and character output. X05 ft_print_com.c explanation. Explain the nested loop structure and the logic for generating and printing combinations. Outro. We've now explored each exercise in the Piscine CO exam, dissecting the code to understand how each function works and its purpose. Remember, practice is key to mastering programming. Try modifying the code, experiment with different logic, and see what you can create. Let's get started. Transition to desktop view with code. XO ft_ft.c. X01 ft_ultimate_ft.c. Moving on to X01, the challenge escalates. We need to modify an integer value to 42 again, but this time through a chain of 9 pointers. The function ft_ultimate_ft showcases the use of multiple levels of pointers. By dereferencing these pointers 9 times, we reach the original integer and set it to 42. This exercise emphasizes the understanding of pointer arithmetic and memory management in C. X02 ft_swap.c. X03 ft_div_mod.c. Next up, X03 introduces us to ft_div_mod, a function that divides two integers and stores the result and remainder into separate variables. This function demonstrates how to perform arithmetic operations and use pointers to store results. Outside the function scope, a crucial skill in C programming. X04 ft_ultimate_div_mod, C. X04 ft_ultimate_div_mod builds upon the previous exercise by modifying the input integers directly to store the division, result, and the remainder. It's a practical example of how functions can alter the values of variables passed by reference, showcasing the power and efficiency of pointer manipulation. X05 ft_put_str.c. X06 ft_strlen.c. In X06, the ft_strlen function calculates the length of a string by incrementing a counter until the null terminator is encountered. This is a fundamental exercise in understanding how strings are represented and manipulated in C. X07 FT underscore rev underscore int underscore tab. C. X07 challenges us to reverse an array of integers. The FT underscore rev underscore int underscore tab function swaps elements from the start and end of the array moving towards the center, a practical application of array manipulation and algorithmic thinking. X08 FT underscore sort underscore int underscore tab.c. Finally, in X08, we tackle sorting an array of integers with FT underscore sort underscore int underscore tab. This function uses a simple sorting algorithm to order the elements in ascending order, showcasing basic algorithm design and the importance of understanding data structures. Closing scene. Happy coding and credits. Thank you for watching. If you found this tutorial helpful, please like, share, and subscribe for more programming tutorials. See you in the next video. Hello, everyone. Today, we're diving into a series of Turbo C projects designed to tackle the C Piscine C01 exam questions. We'll explore each solution nestled within our project directory and break down the code to understand how these tasks are accomplished. Let's get started. Transition to desktop view with code. XO FT underscore FT.C. In our first exercise, XOO, the task is to set the value of an integer pointed to by a pointer to 42. Here's how we do it. We declare a function FT underscore FT that takes a pointer to an integer as its parameter. Inside the function, we use the dereferencing operator asterisk to set the value pointed by NBR to 42. This demonstrates a fundamental concept in C, manipulating the value at a memory address. X01 FT underscore ultimate underscore FT.C. Moving on to X01, the challenge escalates. We need to modify an integer value to 42 again, but this time through a chain of 9 pointers. The function FT underscore ultimate underscore FT showcases the use of multiple levels of pointers. By dereferencing these pointers 9 times, we reach the original integer and set it to 42. This exercise emphasizes the understanding of pointer arithmetic and memory management in C. X02 FT underscore swap.c. X03 FT underscore div underscore mod C. Next up, X03 introduces us to FT underscore div underscore mod, a function that divides to integers and stores the result and remainder into separate variables. This function demonstrates how to perform arithmetic operations and use pointers to store results outside the function scope, a crucial skill in C programming. X04 FT underscore ultimate underscore div underscore mod C. X04 FT underscore ultimate underscore div underscore mod builds upon the previous exercise by modifying the input integers directly to store the division, result, and the remainder. It's a practical example of how functions can alter the values of variables passed by reference, showcasing the power and efficiency of pointer manipulation. X05 FT underscore put str.c. Moving on to X05, we write a function FT underscore putstr that prints a string to the standard output. This function iterates through each character of the string until it reaches the null terminator, illustrating the concept of string manipulation and the use of the write system call for output. X06 FT underscore strlen.c. In X06, the FT underscore strlen function calculates the length of a string by incrementing a counter until the null terminator is encountered. This is a fundamental exercise in understanding how strings are represented and manipulated in C. X07 FT underscore rev underscore int underscore tab C. X07 challenges us to reverse an array of integers. The FT underscore rev underscore int underscore tab function swaps elements from the start and end of the array moving towards the center, a practical application of array manipulation and algorithmic thinking. X08 FT underscore sort underscore int underscore tab C. Finally, in XO8, we tackle sorting an array of integers with FD_sort_int_tab. This function uses a simple sorting algorithm to order the elements in ascending order, showcasing basic algorithm design and the importance of understanding data structures. Closing scene. Happy coding and credits. Thank you for watching. If you found this tutorial helpful, please like, share, and subscribe for more programming tutorials. See you in the next video. Opening scene. Hello, fellow coders. Today's journey through the realm of C takes us to the Piscine CO3 exam questions, where we'll master the art of string manipulation using Turbo C. From comparing strings to searching substrings, we're covering it all. Let's unravel these functions together. Transition to desktop view with code. XO, ft_strcmp.c. Kicking things off with XO, we have ft_strcmp, a function that compares to strings. It iterates through each string until it finds a differing character or reaches the end. The function then returns the difference between the ASCII values of the first pair of differing characters. This is essential for sorting or comparing strings in C. XO1 ft_strncmp.c. Next, in XO1, we delve into ft_strncmp, which similarly compares to strings but only up to n characters. This adds a layer of control, allowing us to limit the comparison to a certain length. It's particularly useful for comparing prefixes or fixed-length string fields. XO2 ft_strcat. C. XO3 ft_saint or nc@.c. In XO3, ft_strcat builds on the concept of concatenation by limiting the number of characters appended from the source string to NB. It ensures that we don't overflow the destination buffer, providing safety when combining strings of unknown length. XO4 ft_strstr.c. Closing scene. And credits. Thank you for tuning in. If you found this guide helpful, please like, share, and subscribe for more programming insights. Don't hesitate to experiment with these functions, explore their nuances, and until next time, happy coding! Opening scene. Hello, programmers. Today, we're diving into the Piscine CO4 exam questions, focusing on essential functions in Turbo C that play a crucial role in handling strings and numbers. Whether you're learning C for the first time or brushing up on your skills, these functions are foundational to becoming proficient in C programming. Let's get started. Transition to desktop view with code. XO ft_strlen.c. First step. XOO brings us ft_strlen, a function that calculates the length of a string. It iterates through each character of the string until it encounters the null terminator, 0, counting each character along the way. This function is a building block for string manipulation, allowing us to understand and work with the dimensions of textual data. XO1 ft_put_str.c. XO2 ft_put nbr.c. XO3 ft_atoy.c. Lastly, XO3 introduces ft_atoy, which converts a string to its integer equivalent. It skips any whitespace and checks for a sign indicator, plus or. Then accumulates digits into an integer until a non-digit character is encountered. This function is critical for parsing numerical inputs from strings, enabling the program to work with user input or data stored in textual form. Closing scene. And that wraps up our walkthrough of the Piscine CO4 exam solutions. Each of these functions, from ft_strlen to ft_atoy, plays a critical role in the manipulation and interpretation of data in C programming. Mastering these will not only help you ace your exams, but also lay a solid foundation for tackling more complex programming challenges and credits. Welcome back to our programming channel, where we delve deep into the world of C programming. Today, we're tackling the Piscine CO7 exam questions, focusing on dynamic memory allocation, These questions challenge us to create functions that dynamically allocate memory for new data structures. So grab a cup of coffee and let's get started. Transition to desktop view with code. XO ft_saint rdep.c. First on our list is ft_strdep, a function that duplicates a string. Starting with determining the length of the source string, we allocate enough memory to hold a copy, including the null terminator. Then we copy the string character by character into the newly allocated space. Finally, we return a pointer to this new string, effectively creating a duplicate in memory. XO1 ft_range C. Next, we have ft_range, which creates an array of integers, each representing a consecutive value between a minimum and a maximum. If the minimum is greater than or equal to the maximum, we return null to signify an empty range. Otherwise, we allocate memory for the array and fill it with integers from min to max, not including max itself. This function demonstrates how to generate and work with ranges of numbers dynamically. XO2 ft_ultimate_range C. XO3 ft_strjoin.c. Closing scene. And there you have it, a deep dive into the dynamic world of memory allocation in C through the lens of the Piscine C07 exam. Each of these functions showcases a different aspect of dynamic memory management, from duplicating strings to creating complex data structures. Mastering these concepts is crucial for advanced C programming and opens the door to creating more efficient and flexible applications. And credits. Intro. Hello, fellow programmers. Today, we're diving into the fascinating world of Turbo C as we tackle the Piscine C08 exam questions. We've prepared several projects to guide you through, and we'll be exploring the intricacies of each solution, starting with the XO4. Let's get into the heart of C programming and master these concepts together. Body. In our Piscine C08 folder, we find various exercises, each in its subfolder. Today, we focus on XO4, which includes two crucial files, ft_stock_stir, h and ft_strs_to_tab.c. Let's unravel the mystery of ft_strs_to_tab. See, line by line. First, we include necessary headers, STIO, for standard input and output operations, and stdlib, for memory allocation functions. Then, we include our custom header ft_stock_stir, h, which defines the structure we'll be using. The heart of our program is the ft_strs_to_tab function, which converts an array of strings into an array of structures. But before we dive into it, let's understand the support functions, ft_stir_len and ft_strdep. ft_stir_len calculates the length of a string. We initialize an integer I to 0 and iterate through the string until we hit the null terminator, incrementing I at each step. This function returns the length of the string. Next, ft_strdep duplicates a string. We start by determining the size of the source string. Then, we allocate enough memory for a copy, including space for the null terminator. We copy each character from the source to the new string, ensuring to end the copy with a null terminator. Now, let's discuss ft_strs_to_tab. This function aims to transform an array of strings into an array of s_stock_str structures, each holding information about the original string and its duplicate. We start by declaring an integer I for iteration and a pointer array to s_stock_str for our array of structures. Memory is allocated for this array based on the number of input strings plus 1 for a terminating null structure. If memory allocation fails, we return null to indicate an error. Otherwise, we loop through each input string, populating our structure with the string size, the original string, and a duplicate. After populating each structure, We mark the end of the array with a structure initialized to zeros. Finally, we return our array of structures. Outro. And there you have it. A deep dive into the ft_strs_to_tab function for the Piscine CO8 exam. Understanding each line and its purpose not only helps us tackle this specific problem, but also enhances our overall programming skills. Stay tuned for more exercises explained, and happy coding! Intro. Welcome back, programmers! Today, we're embarking on another exciting journey into the world of Turbo C, focusing on the Piscine CO9 exam questions. We've meticulously prepared several projects to guide you through these challenges. By dissecting each function within the XO and XO2 folders, we aim to deepen your understanding of C programming. Let's dive in body. Our adventure begins in the Piscine CO9 folder, where we find a treasure trove of exercises, each meticulously organized into its respective subfolder. Today, we zero in on XO and XO2, home to our fundamental C functions and a complex string manipulation task. Let's start with the basics in XO, where functions like ft_putcher, ft_putster, ft_st are CMP, ft_strlen, and ft_swap lay the foundation of our C programming toolkit. Each of these functions plays a critical role in manipulating data types and strings, crucial for any aspiring C programmer. ft_putcher is our first hero, elegantly writing a single character to the standard output. It utilizes the write system call, showcasing how simple operations form the building blocks of more complex programs. Following closely is ft_putster, a function that extends ft_putcher's logic to iterate over a string and display each character. It cleverly calculates the string's length to ensure the entire message is conveyed. In the realm of comparison, ft_st or CMP serves as a judge, meticulously comparing to strings character by character until a difference is found or the end is reached, returning the difference between the ASCII values of the divergent characters. ft_strlen embarks on a quest to determine the length of a string, incrementing a counter as it traverses each character until the null terminator is encountered, showcasing the importance of understanding string basics. Transitioning from strings to variables, ft_swap demonstrates the power of pointers by exchanging the values of two integers, highlighting a fundamental concept in C programming, memory manipulation. As we venture into XO2, the complexity escalates with ft_split, a function designed to dissect a string into an array of words based on specified separators. This function embodies the essence of string manipulation, from identifying word boundaries to dynamically allocating memory for each word, illustrating advanced concepts such as pointer arithmetic and dynamic memory allocation. Outro. And there we have it, a deep dive into the core functions that form the bedrock of C programming, as presented in the Piscine CO9 exam. These functions not only serve as essential tools in your programming arsenal, but also illustrate fundamental concepts that underpin the C language. Stay tuned for more detailed explorations of each exercise, and happy coding! Intro. Hello, programming enthusiasts! Today, we're tackling the Piscine Ratio exam, a challenge that tests our ability to use basic C programming concepts to create a simple yet intriguing output. We'll dive into each part of the code found in our Piscine Ratio folder and break down how each function contributes to the final result. Let's start coding our way through this challenge. Body. We begin our journey with the backbone of our project, the ft_putcher C file. This file contains a single function, ft_putcher, which writes a character to the standard output. It's a straightforward function that utilizes the write system call to display a character on your screen. Understanding how to output data is crucial in programming, and ft_putcher provides a perfect starting point. Next, we explore the main C file. This is where our program starts execution. Inside, we find the main function, which has a single responsibility to call the rush function with two parameters, 5 and 5. These parameters dictate the dimensions of the pattern we're about to draw. The main function is the entry point of our program, showcasing how functions can be orchestrated to achieve a goal. Our adventure leads us to the heart of the project, Rush Show. See, this file is where the magic happens. The rush function takes two integers, x and y, representing the width and height of a rectangle, and prints a specific pattern to the screen using the ft_putcher function. The function first checks if the provided dimensions are valid. If they are, it iterates over each row and column, deciding whether to print a space, a dash, a vertical bar, or a corner based on its position. This logic is encapsulated within nested loops, demonstrating the power of iteration and conditionals in creating complex patterns from simple rules. The beauty of Rush.c lies in its ability to dynamically create a rectangle of any size, filled with spaces and framed with dashes and vertical bars, without characters as corners. It's a fantastic example of how basic programming constructs like loops and conditional statements can be used to solve problems and create visually appealing outputs. Outro. And there you have it. By dissecting each file in our Piscine Rush Show project, we've uncovered the basics of C programming. From outputting characters to using loops and conditionals to create complex patterns. This exercise not only tests our understanding of these concepts, but also challenges us to think about how they can be applied to create practical and interesting programs. Keep experimenting with different values and see what other patterns you can create. Happy coding! And see you in the next tutorial. Intro. Hey everyone! Welcome back to our programming tutorial series. Today, we're diving into an exciting challenge from the Piscine Rush 01, a puzzle solver written in Turbo C. This project includes a variety of files, each serving a specific purpose in solving the puzzle. Whether you're new to C or looking to refresh your skills, you're in the right place. Let's get started. Body. Our project is structured into several key files: input_validation, C, print.c, solver.c, and validation.c, along with a header file clues, H for defining our structures and function prototypes. Let's explore each field's role and how they work together to crack the puzzle. Input_validation.c. First up is input_validation. See, this file ensures that the puzzle input meets our requirements. It includes functions to check for whitespace, count the number of valid clues, and copy these clues into our puzzle structure. It's crucial for setting up our puzzle correctly and ensuring that we have a valid starting point. Print.c. Next, we have print.c, responsible for outputting the puzzle to the user. Whether it's showing the current state of the puzzle or debugging information, print.c makes it easier to visualize what our program is doing. This is especially useful for understanding how our solver progresses towards a solution. Solver.c. The heart of our project lies within Solver. C. This file contains the logic to iteratively or recursively explore possible solutions to our puzzle. By placing numbers according to the puzzle's rules and checking if the current state is valid, it works its way through the puzzle until a solution is found or all possibilities are exhausted. Validation.c. Validation is crucial, and validation. C takes care of this. It includes functions to check for duplicates and validate the view from each side of the puzzle, according to the clues. This ensures that our solution not only fills the puzzle, but also adheres to the specific rules defined by the clues. Outro. And there you have it, a comprehensive walkthrough of the Piscine Rush 01 Turbo C project. By breaking down each file, we've seen how input validation, puzzle printing, solving algorithms, and validation routines all play a vital role in tackling this challenge. Remember, programming is all about problem solving and breaking down complex tasks into manageable pieces. I hope this video has shed some light on how to approach such puzzles and refine your programming skills. Happy coding, and see you in the next tutorial. Intro. Hello, and welcome back to our programming tutorials channel. Today, we're diving into the C Piscine Shell 1 exam, where we'll unravel the mysteries of shell scripting. From manipulating environmental variables to parsing command outputs, we'll go through several shell scripts designed to perform a variety of tasks. Let's get started and learn how to write effective shell scripts. Body, print_groups dot. Our journey begins with print_groups. This script lists the groups the current user belongs to, formatted as a comma-separated list without spaces. It uses the groups command combined with st for replacing spaces with commas, and tr to remove any trailing new lines. This is a great example of piping commands together to format output precisely. Find_stash. Next, we have find_stash. This script searches for files ending with sh and prints their names without the directory path or sh extension. It uses find to locate files and basename with the s option to strip the extension. This demonstrates the power of find for file operations and basename for manipulating file names. Count_files dot. Moving on to count_files. This script counts the total number of files and directories in the current directory and its subdirectories. It combines find with wc all to count lines, showing the total count. This script is a simple yet powerful tool for inventorying file system elements. MAC dot. In MAC dot, we extract the MAC addresses of all network interfaces on the machine using ifconfig and awk. By filtering ifconfig output with awk, we can isolate and print just the MAC addresses. This script illustrates how to parse command output to extract specific information. Skip dot. Lastly, skip dot shows us how to list files in the current directory, skipping every other file. It uses ls_l combined with awk to print lines based on the line number. This is a clever use of awk as built-in and a variable to process records conditionally. Outro. And there you have it, a walkthrough of the C Piscine Shell 1 exam, where we've explored a variety of shell scripts and their practical applications. Whether you're counting files, parsing output, or manipulating strings, shell scripting is a versatile tool in your programming arsenal. Remember, practice is key to becoming proficient in shell scripting. Experiment with these scripts, modify them, and CW.